So are we going to finish and then go over the homework?
We are, because I know there are a few questions about the homework, and I do have like screenshots of the homework that's going to be due Wednesday. I brought my thing here today in case anybody wanted to hand it in, they can, but it's not due till Wednesday.
I messed up on the
Yeah. But we have just 3 slides by my count, and I want to take a running start at it. So honestly, these were the kind of the 3 different scenarios that we hit on Wednesday. Seems like forever ago, right?
Yes.
Yeah. Just to kind of remind you, we had some. I wrote over here. By the way, I was talking up here, and if you're a Twitter, or you can follow me on Twitter and see. Basically, I take screenshots of the whiteboard. The other thing is, if you don't tweet or whatever, in my course syllabus is a website. I'm sure everybody's on the internet, so you can actually go to this website. This is my course syllabus, and you can see those things too. So over here we had, oh my goodness, so long ago. But we had remember the ELR? Remember I had to kind of say that varies. Darn it. Because on your unit 1, I said it was about 6.5 degrees. Okay, so actually each one of these scenarios vary by ELR. ELR you get by sending up a weather balloon. Okay, and so in this first scenario we have 3 different kind of scenarios depending upon what we call it the profile. What's the temperature doing as you go up? In this case, it's getting colder 5 degrees Celsius for every 1 kilometer that you rise. And we spent some time, actually clear over here on the left is what's showing you what the temperature of the atmosphere is, okay? Then we spent some time talking about, basically, I called it the hot air balloon test, basically comparing the temperature of your chunk of air with what the temperature of the atmosphere is over here, okay? And if it was warmer, then actually we said its tendency would be to rise, like hot air rises. But this first scenario, you kind of see over here, kind of in the middle, the tendency is actually, it's what we call stable. And stable, what does that mean? It means it does not want to rise. Why doesn't it want to rise? Because at each elevation, we did this on Wednesday, at each elevation, actually, that chunk of air is colder than the environment. And we said that this will always be the case if your ELR is less than your WAR. And remember, your WAR is your wet adiabatic rate. And if we go with, and your author has 2 of them, nice guy that he is. And if we go with, this slide actually goes with, it cools at 6.5 degrees Celsius for every kilometer it rises if we have condensation going on. Okay, so actually, remember, I really like these figures. Right here, about 2,000 meters, 2 kilometers, we see a cloud forming. That means that we have condensation going on. And then, so we see it rising and cooling at 6.5 degrees. So it goes from, let's see, no, 6, sorry, 6, I was wrong. Yeah, so let me change this. I said it went from 5 to 6. So it goes, when you see the clouds start to form at 2 kilometers, when it goes to 3 kilometers, it cools from 0 to -6. And then when it goes up another kilometer, from 3 to 4, it cools from -6 to -12, etc. Okay? All right. Just kind of getting a running start at it. Then this actually is, you see right away a few things, okay? You see we sent up our weather balloon, and our weather balloon now told us that the cooling of the atmosphere is 12. The significance of it cooling 12 degrees Celsius for every kilometer it rises is that is a situation in which your ELR, which your weather balloon said, is greater than your DAR. You're like, could you have any more R's? Okay, DAR is the dry adiabatic rate, and that is 10 degrees Celsius per kilometer, which 12 is, so that's cool. The difference here is the tendency. It basically, what I say, passes the hot air balloon, which means at each one of these elevations, okay, if you check the temperature of the air, it is warmer than the temperature of, if you check the temperature of the chunk of air that's rising, it's warmer than the outside. Okay, and here on these last slides, actually we're going to call this situation unstable. If this tendency is to rise, okay, then it's unstable. Right? And last but not least, we have this situation in which it's conditionally unstable or conditional instability. Remember, I kind of have a couple of words for those. Hopefully you can go from conditionally unstable to conditional instability. And the thing here, just going right to the quick, if your ELR, if the weather balloon you send up, okay, tells you that lapse rate is less than 10, which is your DAR, but it is greater than 6, which is your WAR, then by golly, it's going to be conditionally unstable. And my best bet is to say, to me, what one of the conditions is you need to have moisture there. You need to have some sort of condensation. And so actually, we end up with kind of a split sort of personality. We have a tendency lower. Basically, it's stable, and up here, it's unstable. Okay, so that's kind of how that goes. Now, today we're going to finish up this part, and then actually in a minute when we start this chapter, when we start chapter 5, I'm actually going to go to the window and we're going to look at these clouds, kind of give them names, these clouds. Okay, so unstable air, what does that mean? That means the tendency in those slides that we just saw, or we just did Wednesday, tendency is to do this, to rise. It's unstable. I'm going to go ahead and link chapter 4 with chapter 5, if that's okay with you. These will give you clouds that are cumulus, cumulo. I'll just go ahead and, it's usually a prefix. Cumulo sort of clouds happen in unstable sort of situations. I'm going to call these fluffy. Fluffy. Like mashed potatoes, yes.
What do you call it?
Cumulo, so of that sort. Okay. The other type is stable air, and we saw some situations with absolutely stable, okay? Tendency is down, okay? Why? Because the chunk of air is actually cooler than the surrounding. These types of clouds, here in a minute, the beginning of chapter 5, we are going to call these stratus-type clouds. And they're not fluffy, they are flat. Okay? You can get air to rise, but it doesn't want to rise, okay? And it's usually going to be kind of flat clouds. So air that doesn't want to rise, I bet you buy this, okay? If the air, it's kind of like, we have an ongoing kind of, I'll call it kind of positive, we'll talk more about pressure in Unit 3, but we have kind of an ongoing little updraft, okay? And so that's kind of nice, because if we pollute this layer of the atmosphere, it goes up, and we kind of have gentle kind of cycles. Okay, but if you have if the tendency of the air is not to rise, then actually that kind of can put a lid on your cities that are spewing out pollutants. Okay, we talked about temperature inversions. This over here is a temperature inversion. Actually, we're going to talk. Probably the idea of a temperature inversion is going to come up. What does that mean? It means as you go up in the troposphere, okay, we thought as you go up in the troposphere, it should get colder. And so actually, the top part of this profile is showing you that. As you go up, okay, it's getting colder. This right here is actually showing you temperature inversion. As you go up, it's getting warmer. So it gets warmer, and then it gets colder. It goes back to normal. The two types of precipitation we said you can get with a temperature inversion. Do you guys remember what those are? It's not snow and it's not rain. It's sleet. Very good. And hail. No, not sleet. You get hail with cumulonimbus clouds. So sleet and what? Grapple. Freezing rain. That's what I was after. Glaze or freezing rain. And I think I might have mentioned this, but freezing rain is sometimes called glaze. You call it glaze. Yeah, donuts. And sleet is sometimes called ice pellets. Okay, and hail, you threw me off for a minute though. So hail kind of looks like sleet, but hail comes from, not from a temperature inversion. Okay, all right. Okay, so let's take a look at what's due on Wednesday. Chapter 4 looks like this. And some of you guys have already done these. Question 4 and question 6 kind of look similar. All right, so this one you have to use complete sentences. There's not an asterisk. So explain how perspiration cools the skin, and my hint there is latent heat. Remember, we talked about latent heat is when something changes phases, and latent heat in this case is when the liquid, your sweat, is going to a gas. Basically, your hot arm is making this happen, making liquid go to a gas. We're hoping for that. We're hoping liquid will go to water vapor. Okay, and that requires heat. So I say heat or energy required. The next one says, all right, look at these two locations, the dry heat in Phoenix and the humid heat in Tampa. Let's see. I'll ask it like this. How many people, dew point temperature. So remember, dew point temperature, actually, the fact that Tampa's dew point temperature is only, 34 degrees? Okay, which looks like a lot. So we have to lower it 34 degrees Fahrenheit in order to get dew to form. Okay, and this actually, we have to lower it, let's see, 54? Yeah, 54 degrees, yep. So in Florida, you're right, it's easier, so we're closer to the dew point temperature, DPT. So if we're closer to the dew point temperature, what would you say about the humidity? It's up. Yep, it's higher humidity. Yep. And so if this is a higher humidity, higher percent H or RH, okay, does it make sense that when we go to when our bodies try to do this up here, okay, there's already a lot of vapor in the air. Basically, it's not going to evaporate as much. So we're going to feel sticky. Yeah. So that's kind of the thing I'm after. And I'll go ahead and I'll grab these screenshots and put them out under Twitter too. I can do that. Oops, come back. The next one, again, looks at those same two cities, I think. Wrong class. There we go. Oops. Okay, so this one, okay, looks at Phoenix, but now it's Bismarck, North Dakota. Okay, so again, before we look at the questions, let's kind of look at what's given. The current temperature and the dew point temperature. Okay, so we could kind of come up with in this case, we only have to go, 1 degree? 1 degree Fahrenheit within. And the other one is the same, 54 degrees. So which one are we closer to reaching saturation? Which one? Bismarck, exactly. Okay, so do you guys buy this one? That this one has a higher percent relative humidity? Okay. Cool. So that's the answer to A, which has a higher percent relative humidity. Which city has the greatest quantity of water vapor in the air? Well, you would think it's Bismarck, but do you remember where we said warm air holds more water vapor? That's the catch there. Warm air, more water vapor. Okay, and actually it says that you can use your table B to convince yourself of this. But on table B, if you go and find 101 degrees and you go and find 39 degrees, you're going to see that at 101 degrees, it can hold a lot more than at 39 degrees. It's a little tricky, it's a little subtle, okay, but I think what you're going to find when you wrestle with the information on table B is that actually there is more water vapor in Phoenix. Oops, how do you spell Phoenix? Okay, that's what I think. C, in which city is the air closest to the saturation point? You guys already told me. Which one was that one? Yep, I agree. I'm going with Bismarck for C. D, which city does the air have the greatest holding capacity for water vapor? Phoenix, yeah, so it's a little tricky. Put this way, if you were to take both of these cities and you were to cool them down to 38 degrees Fahrenheit. We're going to cool them down to 38 degrees Fahrenheit. Can you imagine, like, I don't know what time of year it is, but I guess Arizona gets 38. I don't know.
Not very often.
Not very often? Okay.
I live there.
But if you were to cool it down to 38, which is well below the point of condensation, you would have a dump load of precip, okay? If you were to cool Bismarck down 1 degree, you would have some precip. This cold air cannot hold as much water vapor as that warm air. It's a little subtle, okay? Okay, let's look at the third one. The third one looks like this, where we talked about how the air is coolest near dawn and it gets warm about 2 or 4 p.m., so that's the red line, that's what you're seeing. And then we actually kind of talked, it's almost counterintuitive, but here about 2 p.m. or so, 2, 3 p.m., okay, you guys would tell me it is the hottest, and you guys would say it's really muggy. But what this supposes is basically the water that's there, there's no more water going into the air. So at the highest temperature, it can hold the most water vapor. So if you do, if you calculate the relative humidity, assuming you didn't get any extra water vapor, which is kind of an odd sort of thing, because a lot of times you do get extra water vapor when it gets warm, okay? But it can hold more at the higher temperature, and you didn't get any new ones, so your percent relative humidity is low. So that's kind of how that goes. So dew point temperature remains constant. That's assuming your water vapor is the same. Okay, so if you want to water your lawn, so this is low RH. This is like, okay, and this is high RH, percent RH.
You want to do it in the morning, right? So you want to do it in the afternoon?
Mm-hmm. It's kind of like the opposite of your sweat driving off. If you don't want the water that you put on your lawn to basically just evaporate, you're going to want it as high humidity as possible. Yep. So I would do it in the morning. Remember in the morning we said, like, if you're camping, you get up and that's when you have your kind of dew gets on you because your air is saturated, because cold air cannot hold as much water vapor. All right. Next one. Okay. So this table is really small, table 4.1, but you can find it. Bless you. Let's just do a few of these.
Thank you.
Bless you. Let's pick the first one. The first one says, all right, we are at 25 degrees Celsius. So on the table, I know it's hard for you to see, but this line right here is 25 degrees Celsius. And then it says that actually we have 10 grams of water vapor in our 1 kilogram of dry air. And it says, what's the relative humidity? So what you got to do is say, well, I know it's saturated. This is a 20 right here. It's hard for you to see. Okay, the max it can hold at that temperature is 20. I got 10. Okay, so actually we did some problems like that. You take what you have, which is 10 grams, divided by what it can hold, which is 20 grams from the table. So this is from the table, and this is what you have. So I get, what, 0.5? And if I want to get it to parts per 100, I can multiply by 100%, and that will give you 50%. That's the answer. Let's do another one, shall we? let's do C. We could do these all day. Change the temperature. Now it's 15 degrees, which, no, it's hard for you guys to see. Oh, yeah, there's a 15 degrees. Good. Here's 15 degrees. It maxes out at 10 grams. Wow, I'm getting kind of a similar vibe from this one. Are you guys? So again, you take what you have, which is 5 grams, and how much it can hold from the table, which is 10 grams. Times 100%. I got 50%. Sorry, it's kind of ugly there. This number is 10. So what do you think? And no, I will not put one of these on your test because you have to divide. I learned my lesson with subtraction. But you should work with them on for homework. Okay? Any questions? Do you guys want to do E, or are you guys okay with that? Thank you. We should do E?
Yeah.
E says it's at 20 degrees Celsius. It has 7 grams of water vapor. At what, remember dew point is a temperature. So basically, this one right here, what's its dew point? Remember dew point temperature. Okay, so what they're saying is I got 7. At what point is it, at what, am I going to cool it down? At what point is it going to be saturated? So what do you think?
10.
I'm liking that. She said 10 because you find 7 here. I know that's little. You find 7 there, and you find out what the corresponding temperature is.
Oh.
I go backwards. Okay, so yeah, the answer is 10 degrees Celsius. I know it's hard to see this. This is 10 degrees Celsius. All right, let's take a look at the last one. The last one, my hint was to draw a picture. And I was kind of describing to somebody, remember anything I draw on the board, I'm going to go ahead and it's under Twitter. So this basically kind of looks like, to me, this is the ground. And remember, we looked at a lot of chunks of air rising. Okay, and it's going to rise according to the dry adiabatic rate until it starts condensing. Okay, so it's going to, first it's going to go the DAR, so actually it's going to get bigger and bigger. And it's going to cool down 10 degrees Celsius for every kilometer it rises. And then it's going to cool according to the wet adiabatic rate, which I'm really thinking we can go with 6 degrees Celsius per kilometer. Not 6.5, 6. Okay, so it says an unsaturated air beginning, so that means there's just a, let's draw my little chunk of air. This is my little cute little chunk of air that's going to rise. Its initial temperature is 20 degrees Celsius. Cool. And we know that as it rises, and each time I draw a circle, assume that that actually is going another kilometer or 1,000 meters. It's going to get bigger and bigger and bigger. And it's going to cool down because it's getting bigger. But at some point, you know, there's 2 different cooling rates. There's the dry without the clouds, 10 degrees Celsius per kilometer, and then there's with the clouds, which is 6 degrees Celsius per kilometer. Okay, so it starts at 20. What would its temperature be at? Oh, tricky, tricky. 500 meters, a half a kilometer? Are we good with that? Yeah, I'm liking it. So this is a half of a kilometer. So you figure if it cools 10 degrees per 1 kilometer, it's going to cool 5 degrees for a half a kilometer. I'm liking that. Now I see I need to change my elevation. So this right here is going to be elevation 500 meters. Yep. So I'm liking it. So I'm going to take 20 minus 5. 15 degrees Celsius. We okay with that? Okay. So if the dew point temperature, the lifting condensation level, so I think I'm, bless you, actually I'm going to kind of have to backtrack. Each one of these circles is not going to be 1 kilometer. I'm just going to go ahead and draw my line there. I'm going to put LCL. Hopefully we're okay. LCL, lifting condensation level. And I'm going to go ahead and try to, bless you. Well, I'm going to have to think through it. So I'm going to go ahead and draw my cloud there. Okay. What temperature? Yeah, so they go ahead, could be. So they go ahead and they say that this temperature where condensation begins, so DPT, dew point temperature, is 11 degrees Celsius. So now what we need to do is say, we need to go ahead and make this chunk rise and cool what, 4 more degrees? Okay, so cool 4 degrees. Okay, and we know that it cools for every entire full kilometer it rises, it cools 10 degrees. This is a hard one. This definitely would not be on your test. So it looks like what, 4/10 of a 400 meters. I'm liking that. Yep. So to me, it doesn't go a full kilometer. It actually goes 4/10 of a kilometer, which is for another 400 meters. Again, I'm going to push that out here.
So it's 900 meters.
Mm-hmm. I'm totally liking that. Yep, you guys got it. So this full distance is 500 plus 400, or 900 meters. Whew! Tough one. So like I said, I'm going to push this on Twitter.
When does it turn into the wet adiabatic, however you say it?
Wet adiabatic rate? Right there at the lifting condensation level. So if we were not going to mess with these fractions of a kilometer, if we're going to go a full kilometer, let's just go ahead and think through that. If it's 11 degrees now, and we go ahead, and if this is 1 full kilometer, it's going to cool from 11 minus 6. Yeah, it's going to cool to, that's not part of the question, but it would be 5 degrees Celsius up there. Yep. And it would be a cloud, not. Yep. Yep. Very good. Okay, so I think that was it. Okay. Now, let's take a look at clouds. Did you guys know, you maybe already knew this, that Walt Disney, when he was coming up with his characters for his cartoons and stuff, actually got some of his ideas from looking at probably fluffy clouds, cumulus clouds, yeah. What's that? Oh, no, I didn't give you chapter 5. But I'll bring it next time, and I'll bring it with the completed slides. I don't have another chapter 5 for you. But this early stuff is just kind of, you'll do fine with it. You'll see what I mean. Okay, so hold that thought, and I'll bring you the completed slides that we covered today. Okay, because I do want to go on. So today, as I was going down the road, I think somebody was like, it was dusty in front of me, and I'm like, oh my gosh, it's like hazy. So I'm like, why does something, when you see haze, what does that mean? Well, basically, there is something between you and what you want to see. We talked about basically light being scattered. So basically, that object that you want to see, some of that light is being scattered by the dust or the fog or something like that. So I've been talking about any time you see, I'll bring them Wednesday, I promise. They'll be completed too. You won't have to fill in any blanks. Okay. Yeah. Or you can follow me to my office and I'll give you a copy then. So either way, but I'll give you complete ones. So I've been talking about this idea. When you see a milky white cloud, hopefully you're okay with the idea that condensation has happened. Basically, water vapor has gone to its liquid state. Okay, so that's one thing. I think, that's all this is talking about. And we're going to be talking more about that kind of liquefaction process, that whole milky white cloud, okay, liquid water particles or snow particles, okay? So if anybody has ever told you don't eat snow, okay,
Oh.
I know. But you can, but...
You can as long as it's not yellow.
Yeah, avoid the yellow snow for sure. But even just regular, beautiful white snow...
Doesn't it pick up, stuff when it comes down?
That's one reason, yeah. As it comes down, it actually has a scrubbing process, which is kind of nice. After a hard rain, you're like, oh, the air smells so fresh. But the other thing is this idea of when it first forms up there, it needs actually what we call a cloud condensation nuclei, abbreviated CCN, cloud condensation nuclei, to get the party started. Okay? Okay.
That's your fault too.
So,
What the heck is going on out there?
I think we're
Nettie
fine.
just came home right down the hallway.
They're fighting.
Nettie!
Okay. I think she's okay. No, she's okay. Okay. Because you're guys going to want to know this for your test. Okay? So we've been talking about a chunk of air cooling to reach the dew point temperature and condensation can begin. But we need to kind of talk more about that condensation, okay? So it first starts with a cloud condensation nuclei, and usually the relative humidity is 100%, okay, when that happens. So cloud condensation nuclei, they'll actually come in two versions. They're most abundant near the Earth's surface, okay? But they kind of come in two versions. Here's mine. I brought this in from before. Isn't that not adorable? Oh, that's sweet. So this is why you don't eat snow, because like this little dust that Snoopy sends up can actually be what we call cloud condensation nuclei to kind of get the party started. Okay. So we have two versions. We have the water-loving cloud condensation nuclei, and those actually mean that they're really anxious to get it done. So actually, you don't even have to be at the dew point temperature for those cloud condensation nuclei to get them started.
So then is it cloud condensation nuclei that has the dust devils that forms them?
No, that would be different. The dust devils that you kind of see like down here on the ground. Well, those dust particles could end up becoming condensation nuclei. So you're on the right track. They could be. The other cloud condensation nuclei are the reluctant party starters. They're what we call hydrophobic. Of course, phobic means fear of. And these are like dust particles or something that generally don't like water, but they will go ahead and make those water vapors connect together, because remember, to go from a vapor to a liquid, we get more connection. That's kind of what the cloud condensation nuclei are doing. But here on Wednesday, probably we'll get to it Wednesday, we're going to talk a bit more about after the party started. Okay, there needs to be more beyond that after the cloud condensation nuclei. But in the meantime, let's talk about your 10 types of clouds. Okay? There are 10. Yes, and you're going to want to kind of know, but I'm going to give you some tips on knowing these 10 cloud types, okay? So first off was something we already talked about. Remember I said the fluffy ones are unstable atmosphere, tendency to rise. Those are cumulo, sort of STI something. And then the flat ones are stable air, they're stratus. So actually we have fluffy clouds and we have flat clouds. Okay, and you're going to see that as usually a prefix, or maybe even a suffix. Then aside from that, it's kind of mixing and matching. You're going to actually, figure from your textbook and on your slides, actually you're going to see kind of 3 elevations. So we have low clouds, we have middle clouds, and we have high clouds. If it's a low cloud, it has no prefix. If it's a middle cloud, it has the alto prefix. And if it's a high cloud, it has like the cirro or cirrus sort of prefix. Okay? The last criteria, there are only 2 clouds that actually dump rain or snow, precipitation. And those 2 clouds need to have NIM or NIMB in them. Okay? So these kind of, we mix and match the flat and fluffy, the elevation, and the precipitation to get 10 cloud types.
So there's like cumulonimbus and cirronimbus.
Mm-hmm. Yep, exactly.
Altostratus.
Yeah. Now, one thing before I show you the 10 cloud types, okay? The fluffy cloud types, there's actually kind of a little device here to know if it's fluffy, is it a low cloud, or is it a fluffy middle cloud, or is it a fluffy high cloud? And it goes like this. Basically, you extend your hand, and if it's really pretty big, about the size of your fist, then that means it's a low cloud. So that's going to be just totally cumulus. If it's about the size of your pinky, I hit my thumb this weekend, like laminate. If it's about the size of your pinky, sorry, this is your thumb. It's about the size of your thumb, it's a middle fluffy cloud. This is a fluffy cloud, so it's alto cumulus. And if it's about the size of your pinky, it's cirrocumulus because it's high up. Yeah. So we have 3 different cumulus: cumulus, altocumulus, cirrocumulus.
So then, the clouds that form foam clouds and tornadoes.
I can see where your mind is.
Thunderheads. Like, I'm just kind of fascinated
Storm
with these
clouds?
because
Yep.
my state has probably the most tornadoes known to mankind.
Yeah. Kansas. That would be it.
Oklahoma.
Oklahoma. Ooh. Similar.
Moore,
Yeah.
Norman, a lot of those towns.
Yeah, Norman, it's
Every
funny
year.
because, not so funny, but Norman, Oklahoma has the National Weather Service's Storm Prediction Center. So it's like the Storm Prediction Center gets hammered by storms.
Yep.
Okay, so here's the 3 different cloud types. You can already see kind of how it's broken up by low, middle, high. Okay, I'm going to start actually with high up there. So high, we said, has a cirrus. So notice kind of from left to right we have cirrus. Okay, that's the highest of high. The cirrus is sort of a stratus cloud. You can tell the difference between cirro and cirrostratus is actually the wind is making this sort of phenomenon. Sometimes these are called mare's tails. Do they look like mare's tails? Okay. So I think that's flat.
When we were in 6th grade, he said that they looked like hair.
They do. I could see that. They look like hair. Kind of wavy hair. I'd see that. These are both flat, though. I like that. And these are higher. Okay, then the next one over there, we have cirro, meaning high, and cumulus, meaning fluffy. So these would be about the size of your pinky.
Those are cool clouds. Those are up there.
They are pretty. And when they kind of get all, they look like tiny little cotton balls.
Yeah.
And sometimes it's called a I'm going to butcher this, but mackerel sky, like a fish, kind of fish scales, mackerel sky. Then we go on to middle clouds. I know these are middle clouds because remember middle has alto. So the middle clouds are only 2. So there's an alto flat, alto stratus, and then there's alto fluffy, alto cumulus. And you can tell the difference between you can tell the difference between cirrocumulus and altocumulus by kind of your pinky and your thumb. And then we get to the low level clouds. Okay, so
Why do
these,
people say holy mackerel?
like a fish, holy mackerel fish, I don't know, maybe it has something to do with like Good Friday. When we start Lent recently?
Ah.
I don't know.
Oh.
Look it up.
Yeah.
Okay. So the low clouds, we have stratus, which the fact it isn't an alto stratus or cirrostratus means that it doesn't have a prefix. So stratus has got to be the lowest. If it doesn't have a prefix, it's the lowest one. This one looks like popcorn?
Yeah, like before every really bad storm,
Yeah, yeah.
for some reason they look like popcorn, and then all of a sudden like it turns into something completely different, more like that.
More like this last one? Yep. Yep. This one here in the middle, it's to me almost kind of like a oxymoronic sort of thing. Strato means flat. Cumulo or cumulus means fluffy, so it's a flat but fluffy. Okay, so it's kind of got some flat, but it's a little bit fluffy, kind of a low cloud. Cumulus clouds then would, since they don't have a prefix, alto or cirro, this would be the size of your fist. Cumulus cloud. And it could go ahead and develop, become more and more unstable, and go ahead and turn into a cumulonimbus cloud. So we have 2 raining clouds. Okay, so you know it's a raining cloud if it has, or precipitation cloud, is if it has NIMB in it. So where'd it go up here? The problem with our raining clouds, and sometimes I have to concentrate, is we have nimbostratus and cumulonimbus. So the whole NIMB kind of goes, it's a prefix for the nimbostratus and kind of a suffix for the cumulonimbus, but that's okay. So nimbostratus means it's raining and flat. Cumulonimbus means it's raining or precipitating and fluffy. Okay, so that was So let me see if they're still out there. Yeah, everybody come to the window. Road trip. And see what you guys think we got. The thing about clouds is sometimes you can see more than one cloud at the same time. Can you kind of, do you think, how many people think that's a high cloud? How many people, yeah, which one? They look kind of similar. How many people think that's a middle cloud? How many people think it's a low cloud? I'm kind of thinking low.
Is it a stratocumulus? That's what it looks like.
Like a stratocumulus?
Yeah.
Yeah, I would buy that. Kind of got some layered, and but it's got fluffy.
I don't think I'd buy a cloud.
Name the cloud like you name a star. That's my cloud, yeah. Might as well. So I'm kind of liking low. I would go with stratocumulus. I would probably also go with just maybe kind of cumulus. So, very good. Well, that's how far I wanted to get today. So I will bring those slides into you tomorrow, Wednesday. And then Wednesday we'll kind of pick up looking more at cloud types and then go on to something harder.